Okay, welcome back to the course on polymer chemistry, and in today's class we will discuss we will basically continue our discussion we are having in polymers in solution, and the topics we plan to cover today. This lecture is cohesive energy density and solubility parameter, how we can use the knowledge from solubility parameter and we can estimate or we can predict the solubility behavior of a polymer in a solvent, and then we will follow up our discussion with phase separation behavior of polymer solutions. Now, let us begin just recapping a few minutes what we discussed in last class or last lecture. Now, this is what we found. We derived that Florey-Huggins equation where this is Gibbs energy of mixing given by two terms. This term was coming from purely combinatorial entropy, and this is always negative. So, this is always favors mixing. Okay. This has always gives you negative contribution towards Gibbs energy of mixing. So, it always favors mixing, and this is coming from a combination of enthalpy and entropy change due to polymer solvent contacts, and it will decide because it is always negative and always contribute in favor of mixing. So, the value of this basically determines where polymer will mix or become soluble in a solvent or not, and if the value becomes less than 0, negative, obviously mixing will happen. If it is positive and large, no mixing, and if it is slightly positive, small, I did not change from last time. So, this is if it is slightly positive and the value is small, then it depends between the competition of these two which will decide whether the polymer will go into solution or not. In dilute polymer solution, we have found that the excess contribution excess chemical potential, we got this relationship, and at theta temperature this term, the excess contribution of excess chemical potential becomes 0 and the solutions become ideally. If you look at this expression, if this contributes negatively, obviously mu 1, this difference would be lower than the ideal. That means, the polymer will the solution or mixture of polymer and the solvent will be favored. If this is positive, then it will be higher than the value of ideal. So, it will have effect against solution. So, theta temperature this becomes 0. So, the solutions become ideal solution and polymer exists in solution with unperturbed dimension. Now, we will come in a next lecture what is unperturbed dimension, but what does it mean in brief is as if the polymers are present as such without no interference or no interaction on the other polymer molecule or the solvent molecule, which we will discuss what the meaning of unperturbed dimension in details in next lecture. Obviously, as I said that when theta is temperature is theta temperature, the value of polymer solvent interaction parameter chi becomes 0.5. So, the solution behave, the polymer and solvent behaves like ideal solution. If this is if the value of chi becomes lower than half, then the coil expands, the polymer expands in solution, which promotes mixing. Psi was, if you recollect, that this was the entropy parameter. Now, to have this term negative for a positive entropy factor or parameter, T has to be higher than the theta temperature to have mixing, whereas if the entropy factor is negative, then T has to be lower than the theta temperature to have mixing possible. And the other cases where the opposite case or reverse case where chi polymer solvent interaction parameter is higher than 0.5, it acts against mixing. Just to give few data for some polymer solvent system having different values of I and theta, let us look at some data of different polymers and with different solvents. As we are mentioning, for this all these cases the interaction parameter value chi is less than 0.5. That means, this is all these examples we are talking about favoring mixing. So, as I mentioned, if psi is positive, then for mixing to happen temperature has to be higher than theta, and examples where there are strong interaction between the solvent and the polymer, the entropy factor becomes negative. In that case, the temperature has to be lower than the theta temperature to have the mixing possible, and these are the two examples where psi factor is negative and T has to be lower than theta to get the mixing possible. Now, let us move to the one more topic on solubility, which is determined by cohesive energy density and solubility parameter. Now, if you look back the Florey-Huggins expression, you have two terms. First term is from combinatorial entropy, which you can predict theoretically if you know the volume fractions of the polymer and number of moles of the polymer molecules. The second term, which actually determines whether the polymer will get solubilized in the solvents, you need to find out the value of that, and there are some approaches from different scientists has been made, and one of the important contribution from this towards this is by Hildebrand, who basically introduced the concept of cohesive energy density and relations to solubility parameter. This is a simple way to predict the solubility of polymer in a solvent, and miscibility, it also can predict the miscibility behavior of polymer system, and it also can, because it can determine or predict the solubility behavior of polymer, it can also simultaneously detect the solvent resistance behavior of the polymer. It mainly useful for as we will see that it is mainly useful for nonpolar solvent and nonpolar amorphous polymers. It is not very useful for polar molecules and polar solvents. It's basically a semi empirical approach as suggested by Hildebrand, following the principle like dissolve like. This means basically, as we know that like the polymers which are a similar structure or similar sort of interaction behavior with a solvent will dissolve in that solvent. Quantitatively, this cohesive energy density is defined by this, which is delta E V is the molar energy of vaporization. It can be written by this expression also, where delta H V sub V is the molar energy of enthalpy of vaporization. This is molar energy of vaporization, this is molar enthalpy of vaporization, and V is the molar volume of the substance. Now, as you know, cohesive energy is basically it gives idea about the interaction or the force of attraction between the similar type of molecule. So, if the cohesive energy density is higher, then the attraction or the interaction between the similar molecules is higher. So, as we know from our previous understanding that cohesive energy is the energy of interaction between the similar molecules. So, higher cohesive energy density means higher attraction between the molecules. Now, Hildebrand defined the term solubility parameter, which is basically square root of the cohesive energy density. So, it is given by this expression, and this is what we are looking for. The enthalpy of mixing is given by, if you know the values of the solubility parameter, then the enthalpy of mixing can be obtained by this expression. We know the contribution from the combinatorial entropy, which is always favoring mixing. Now, this is term will give you the enthalpy of mixing, but the way this expression has been proposed, it always gives the enthalpy of mixing. Enthalpy of mixing del H sub m is always positive or 0 if delta 1 is equals to del 2. So, the drawback of this approach is that it cannot predict any negative enthalpy of mixings, which sometimes happen if there are strong specific interaction between the polymer and the solvent. The Vm is the average molar volume of the polymer and the solvent. So, if you think about the Gibbs energy of mixing, which is delta H minus T delta S. So, obviously, the lower is the value of delta H, the better is the mixing, and if it is negative, then obviously it favors most. But in this case, because it is positive or 0, then the case where delta H mixing would be 0, it will be most favorable for mixing, and if it is positive, then the lower is the value of delta H sub m, it will be better for mixing. So, as Hildebrand suggests that compatibility between component 1, which is the solvent, and component 2, which is the solute, the polymer in this case, arises as you have the less differences between the solubility parameter of the two components. So, if they are same, that is the base case where delta H m would be equals to 0. Now, we have seen before that the polymer solvent interaction parameter is actually have two component, the entropic component and enthalpic component, and it can be shown that enthalpic component can be expressed by this expression as well. And this term entropic contribution towards the polymer solvent interaction parameter is most cases it has value of 0.2. Okay. So, if this is close to 0 or at least less than 0.3, then chi would be less than 0.5, which means it will promote mixing, and which means the closer the values of delta 1 and del 2, then obviously the difference it will be nearer to 0, the chi h value would be nearer to 0. So, from this expression also you can predict that the polymer solvent interaction parameter would be lower than 0.5, which means the polymer will promote or it will dissolve in the solvent you are using. Now, as I said before that this works well for polymers or for a non-polar solvent and non-polar amorphous polymer. It is not valid for crystalline polymers because this expression or this approach we are talking about talks about liquid solvent and liquid polymer, means amorphous polymer. So, if you want to dissolve a crystalline polymer, then you have to also include the contribution for the enthalpy of crystallization. So, in this case that enthalpy of crystallization is not taken into account. So, that is why this approach is not valid for crystalline polymers, this is valid only for amorphous polymer. In case of polar solvent, you can have specific interaction between the polymer and the solvent. For example, it can have hydrogen bonding, it can participate in electrostatic interaction, and which we can think that if there is specific interaction like hydrogen bonding or electrostatic attraction between the polymer and solvent, then there is a possibility that del H mixing would be negative, and that as this approach solubility parameter approach does not predict any value of any negative value of delta H mixing. So, this is not valid for polymer non-polar polar polymer and polar solvent. Usually it is usually valid for non-polar solvent and non-polar amorphous polymer and non-polar solvent. Now, how to get this delta value, the value of the solubility parameter? Obviously, as we you can recollect, this the delta can the cohesive delta is the cohesive square root of cohesive energy density, and cohesive energy density can be found from molar energy of vaporization or molar enthalpy of vaporization. For liquids or for solvents, you can experimentally determine the molar enthalpy of vaporization and the molar volume. So, you can get the cohesive energy density and the value for the solubility parameter as well. But for polymers, because they cannot be vaporized or polymers are not vaporizable, you cannot experimentally get the value of solubility parameter for polymer because they are large in size. So, they are the value of delta, the solubility parameter of polymers are typically determined indirectly, and it is basically following the approach we took. The delta AHM becomes 0 as delta 1 and delta 2 becomes same. So, polymers are added. If you are talking about linear polymers, then the intrinsic viscosity of that polymer is measured in several solvents, several common solvent, and the highest or the maximum intrinsic viscosity in the solvent which the polymer gives, the solubility parameter of the polymer is taken as the same as the solubility parameter of that particular solvent. So, basically this indirectly telling that the delta 1 and delta 2 are same. So, this gives giving the maximum solubility or maximum intrinsic viscosity for that polymer. If the polymers are cross linked or gelled, then we do the same experiment, take the polymer and do a series of put the polymer network in series of solvents and find out the maximum swelling ability. So, if where the interaction is maximum, the maximum swelling happens. So, we take the solubility parameter of that particular solvent as the solubility parameter of the given polymer. The value of solubility parameter of polymers can be also indirectly obtained from group contribution method. As you know, group contribution methods are utilized to find out theoretically the value for several other parameters, several other properties of polymers, and this solubility parameter also can be obtained by group contribution method, and this is how it is done. There are particularly the solubility, this is done theoretically. Delta is this is F is the contribution from or the value for different groups. Okay. So, if you can divide or dissect the polymer into different parts, that these values for F are available in literature. So, you can add those, and this is molar volume. So, you can also write this as in density and molecular weight. Now, f can be a f value of f is given by small and Hoy, and let us look at one example. Say we take PMMA, polymethyl methacrylate, the structure of which is, as you know, this is the structures. So, how many groups it has? You have to count groups. There are 2 CH3 groups. So, 2 CH3 groups, 1 CH2 group. So, 1 CH2 group, 1 CO group and 1 quaternary carbon. Okay, so, these are the groups there in this polymer, and the values of these are supplied. The contribution of these groups are already tabulated or theoretically found out by scientists like Small and Howe. So, you have to just take those values and add up to get this value and then get the solubility parameter. The F value which has been supplied in the literature for this is 303.4. So, this gives you 2303.4 is 269. So, you sum up, you get 69.5. So, delta would be given by multiplied the density 1.19 and by the molar mass of the repeat unit. Okay, now look at these values of the groups. As I said that this gives this basically the solubility parameter is basically the square root of the cohesive energy density, and cohesive energy density is nothing but a measure for the interaction or attractive interaction between the molecules. If there are polar molecules, obviously there are attraction between the similar molecules become higher. So, the contribution become higher, and if the volume becomes higher, if there is no polar groups, the volume becomes higher, there is more van der Waals forces between them, which also increases the cohesive interaction between the groups. So, this CH3 has higher than CH2 than the quaternary carbon atom. This is directly related to the volume, the size of the group. So, as the size increases, the van der Waals forces increases. So, van der Waals attraction increases. So, the value of or contribution of these groups increases. So, like this you can get the value for this interaction parameter for any of the polymers, because the value of these are supplied by are available in the literature. Now, look at some of the values, some of the polymers and solvent, common solvent like acetone, delta value 20.3, CCl 6, let us example of take few polymer. like polystyrene, this is some polymers. Polystyrene 18.5 and say bisphenol A polycarbonate is around 19.5 to 20. Now, obviously, if you look at this number 19.5 and to 20, this number 19.5 to 20, obviously, look at these solvents. Now, as we have seen that if the delta value of the polymer is closer to the value of the solvent, that of solvent, then it will promote mixing or the polymer will be soluble in that solvent. So, polycarbonate will obviously become soluble in chloroform, it is 19.5 and 19 and 19.5. Obviously, polycarbonate will not be soluble in methanol, water or some of the very non-polar solvents, so cyclohexane, carbon tetrachloride, xylene and so on. Acetone 20.3 is basically this polycarbonate becomes soil, it is not very good solvent for polycarbonate, but it is it is not also very non-solvent either. So, the solubility of polycarbonate is very low, but it is not 0 in acetone. So, it basically if you know the solvents and the value of polycarbonate, you can predict, you can estimate the whatever you want, which application. For example, if you want to use some medical devices, in medical devices like syringes and some other medical component where you in most cases before use they are sterilized by applying some spirit, rectified spirit which contains alcohol. Now, if you know the solubility parameter of that alcohol, then you know what are the, you can estimate or you can basically zero down or narrow down the choices of your polymer which will not be soluble in that alcohol, which will be used for wiping those or sterilizing those equipment. So, you can basically reduce your number of experiment which you can or your choice of polymers by have a prior knowledge of solubility parameter and the value of solubility parameter solvent and polymer. Some cases these rubber gaskets are used for sealant in maybe in aircraft application where the sealing is very important. Now, obviously, they come or in case of car also the sealants are very important. So, obviously, they come in the contact of the petroleum vapors or they come in contact with this liquid fuel. Now, if those rubbers or the sealants which are made of rubbers actually get swollen, then there would be leakage or there in that sealing method. So, you do not want your material, rubber material to swell in that particular gasoline or liquid fuels. So, you should choose a polymer which would be non-soluble polymer in that environment. So, if you have prior knowledge of your solubility parameter of the polymer and solvent, then you can narrow down the polymers before you go for the exact trial. If you look at the polystyrene, value of polystyrene, obviously polystyrene will not soluble in water and methanol, but polystyrene almost soluble in most of these solvents. So, it actually gives you idea, it does not give you exact sort of solubility behavior, but this gives you guideline or help you to understand what is the solubility, predict the solubility of a polymer in a solvent. Okay, now, let us move to the next topic where we talk about the polymers phase separation behavior of polymer solution. And again going back to the Florey-Huggins expression, Florey-Huggins equation, this gives me energy of mixing. Now, if you want to convert it to gives energy mixing per segment or per unit cell per lattice site, then we will divide by the number of segments, total segments or number of lattice site. N1 is for the solvent and this is for the polymer. So, you divide that and you get this as another expression for the Florey-Huggins expression, where this gives free energy of mixing expressed in terms of per segment of the polymer molecule. Now, this gives the behavior of or the how the Gibbs free energy of mixing per segment varies with say one of the compositions. If you in this case phi 2, phi 1 can be converted to phi 2 easily. So, if you plot say del G mixing, if you plot del G mixing per segment, you can get from this expression of what we just saw in this case. From this expression we will tell you that it will give two general type of variation of Gibbs free energy expression with in this case say phi 2, the volume fraction of the polymer. Now, let us consider this case, the temperature is T5. Now, in this case, if you take any point, say I take this point. Now, if this has to spontaneously phase separate to any of the other two compositions, say this composition and this composition 2 point. So, I consider a solution which corresponds to this particular phi 2. Now, if that has to spontaneously phase separate into two other composition, obviously one has to be polymer rich and this one, and other has to be solvent rich, left hand side. Okay, phi 2 comes down. You can take any 2 point. Now, if that process of phase separation, spontaneous phase separation happen, the delta G mixing of that process would be given by the value of this, okay, which is the distance between the interaction point of the tie line. This is tie line. Now, tie line is the line, straight line connecting 2 points in that curve, and this line which is a vertical line parallel to the y axis. Now, this the value of this gives you the Gibbs free energy mixing. I am telling you again that the value of this gives you the Gibbs free energy of mixing for the process of separating a composition corresponding to this to two composition corresponding to this and this. Okay. Now, this value if you can see for any of these points is positive, which means that this process of spontaneous phase separation is thermodynamically not feasible, which also means that each point or each solution in this line corresponds to different phi 2, they are all stable. So, that means the polymer and the solvent is soluble across composition. So, if you take polymer and dissolve in the soluble in the solvent, it will be soluble for that particular temperature, in this case T5, for any at any composition. Okay. It will not phase separate to any two composition having polymer rich and solvent rich phases, as that is thermodynamically not feasible. Now, consider another temperature T1, you get this type of, this is another general type of curve. Now, the region this side below this point, say I write C and say point D, below the left hand side C and above D is similar to this expression. So, all the composition will be stable. So, you get soluble polymer will get solubilized in the solvent in this range and in this range, okay, exactly like this. Now, look at another composition here, any point here between this and this point, any point in this curve, this is the tie line. So, if this has to phase separate, this solution having polymer mole fraction of this value, if this is to phase separate two composition having polymer mole fraction corresponding to this and this, the Gibbs free energy mixing would be given by this value, and that is negative. Okay. So, which means that between this point and this point, between this point and this point, any composition which immediately phase separate and come to these 2 points. So, if you have any solution having phi 2 value in this region, immediately they will phase separate and form 2 equilibrium solution. Okay, to equilibrium phase. One is polymer rich, one is solvent rich. Okay. Now, look at a point here, any point between these 2 lines, this point and this point, and this point and this point. So, this is E F. So, any point between C and E and F and D. Now, if this has to phase separate to any of the slight changes in the composition, say this point and this point, it will be similar to this curve. Okay. Same in this case, but if this is to phase separate, if I consider this point which has this value of phi 2, if this has to phase separate into 2 phases having composition between this point and this point, then obviously delta G mixing would be positive. So, that will be unfavorable. But if this composition is phase separate into a point here and here, the delta G would be negative. So, it will spontaneously phase separate. So, if this any point in this region, any composition, any solution would be stable for small change in composition, but it is not stable for a large change in composition beyond this point. Okay. So, this is a region of metastable region, where the composition are stable only for slight change in composition. So, this is metastable region. So, these regions are metastable C to E and F to D, and any composition between E to F is completely unstable, which will immediately phase separate into C and D, and any composition between this point and C and D to end would be stable. Okay. They will be clear solution. This is the inflection point. This is the inflection point. Now, if I change some other temperature, the solution will, you can draw some other lines. Okay. And then join these points. Okay. these points to get a bell shaped curve, which I will just come in a minute. Now, let us talk little more about these 2 points and these 2 points C, D and E, F. Now, delta G mix, I can write delta mu 1 plus x 1 x 2 is the mole fraction, delta mu 2, whereas delta mu y is mu y minus mu y 0. It can be written as G is a extensive quantity. So, I can write x 2 delta mu 1 plus x 2 delta mu 2 . So, if you plot delta m versus x 2, you get the slope as delta mu 2 minus delta mu 1, and the intercept will be at x equal to 0 delta mu 1 and at x 2 is equal to 1, you will get delta mu 2. Those are the intercept at x 2 is equal to 0 and x 2 is equal to 1. Now, if I want to do it for delta G m star, which is first segment, and phi 2, we can easily imagine that the slope at any point of that curve would be mu 1, and the intersect at phi 2 0 would be delta mu 1, which is mu 1 minus mu 0, and at this is the intercept at phi 2 is equal to 1 would be delta mu 2 x. Okay. This is just simple mathematics, you can find out that. So, what means that if you plot this delta G m versus phi 2, then the slope will be given by this and the intercept would be given by these values. Now, if you look at these 2 points, the tangent for those 2 points would meet at the same points. Okay. Which means they must have a common tangent. So, these 2 points must have a common tangent. So, and as the slope is given by this, which will also mean that mu 1 for the solvent at point C will be equals to mu 1 at D, and mu 2 at point C would be equals to mu 2 at D. These 2 points will have same slope and have a common tangent. If they are common tangent, then the slopes will be same, and from the slope we have already seen, we can write that mu 1 C equals to mu D. So, the chemical potential of the solvent in this point is same as this point, so as the chemical potential of the polymer in this point and this point, which means that C and D are two equilibrium composition, and we name this as binodal compositions or binodal points. Now, this is between C and D, you can clearly see that C and D are the binodal points where is 0. Between C and E, D and F, the slope is changing in positive way. So, d phi 2 would be greater than 0. And between E and basically F, this is the change of slope. Oh, so I put this. This is slope and this is the rate of change of slope. Okay. This rate of change of is moving in positive direction here and negative direction here, and in the inflection point which is E and F, inflection point E and F would be 0. Okay. These 2 points which are inflection points is called spinodal points. Spinodal points or spinodal composition. Basically, it is the boundary between spinodal points or spinodal composition. This is the boundary between a metastable and a unstable composition. The inflection point is the boundary between the metastable and the unstable compositions, and this gives by this expression. Now, as I was telling little earlier that now you can draw similar lines, like let me try. Okay. And then join this spinodal points and also join the these spinodal points, and you can also join the inflection points to get something like this. I have already drawn, so you can just see from here. So, you can get a curve like this. these are the locus of the binodal points, okay, at different temperature. At different temperature you have different binodal points. So, one temperature you have this, temperature you have this, like this, and one point they will merge. Similarly, this line is the locus for the sphenoidal points, okay. These are the different points for different temperature, and at some points they converge. So, this point, this is critical points is given by convergence of the points of common tangency and the inflection points. Common tangency points are the sphenoidal points and common tangency points are binodal points and inflection points are sphenoidal points. So, by converging you get T c, and so you can write at that point at T c both are 0. Okay, so, you can get this. I hope you got it. These are this line, the solid line is the just your join different binodal points obtained in different temperatures. So, if for one temperature you got binodal points here and here, another points you got binodal points here and here, the another one here and here, you just join them and got a binodal curve. Similarly, this temperature you have sphenoidal points like here and here, this temperature you have here and here, similarly here and here, you join them to get a sphenoidal curve, and this is the point they converge. So, what about these regions then? Any composition above this curve, these solid curves will be completely soluble, okay. They will have single phase. So, any point in this diagram will be having single phase. Any point within this, so basically this region will be completely insoluble, they will phase separate out, and any region, any point here would be metastable point. So, in this single curve, symbol diagram you can get the complete phase diagram. It basically gives you the phase diagram of that polymer in that solvent. So, basically you are plotting at different temperature the composition of the solution. So, at any point in this region you get a single phase which is polymer soluble in the solvent. Any point this temperature and this composition you get two phase polymer pure and in this case you get metastable solution which will be stable towards small fluctuation in the composition, but not in the large fluctuation. So, this basically gives you the phase diagram. You are getting the phase diagram of a polymer in a solvent from that original Flory-Huggins equation. This point you call UCST. upper critical solution temperature. So, above this temperature the polymer is soluble in that solvent at any composition. Below this temperature the polymer is only soluble in that solvent in this composition, left hand side of this point and in this composition, but above this temperature the polymer is soluble in that solvent at any composition. Okay. So, that is called upper critical solution temperature, and you can get the reverse also, and in that case this point called LCST is given called lower critical solution. So, basically below this temperature everything is soluble, polymer is soluble at every composition. Okay. So, if I take that Florey-Huggins expression, this one, and Florey-Huggins expression this one, and write the conditions for sphenoidal is equal to 0, you get the sphenoidal points like 1 minus phi 2 plus and for the critical this is for the critical point, you get again if you do this, we have the expression for delta G m star per segment. If you do this you will get y 2 c for the critical, get 1 plus x 1 plus half. Okay, and from these two you can write the critical okay. So, this is just pure mathematics from getting this expression from Florey-Huggins expression which we got earlier for the per segment gives energy fixing per segment. So, you can get this expression. What we will do, we will just in the next lecture we will take this and just complete the discussion of our phase separation of polymer solution, and then we will look into it that how the molecular weight or the size of the polymer determine the solubility of polymer, and which can be utilized to fractionate the polymer of different molecular weight. We will just start from this in next lecture.